I'm Bing Fan from Carnegie Mellon University, and today I'm going to present the work, a system called MemC3, which is an enhancement of Memcached. And this is a joint work with my advisor, Dave Andersen, and also Michael Kaminsky from Intel Labs. So Memcached is nowadays used widely and more. I'm sure you will be more convinced after the next talk. But in this talk, I'm going to focus on the single node performance and also the single node storage overhead. So the storage overhead is measured by how many bytes to store each item on average. And the performance is measured by how many inquiries you can process per second. And in this space, there are some existing work, of course. And a common practice of this work is trying to use sharding to improve performance. By sharding, I mean to partition the data to different nodes or to different cores. So in this way, we can eliminate the inter-thread synchronization problem and get a better performance. Wow, this is good if the workload is uniform distributed. However, under skilled workloads, those heavy hitters in the workloads may create some hotspots. And also, the memory efficiency is not really addressed in this kind of problems. So we took a different approach, and we tried to explore the possibility to use advanced data structure, especially compact and concurrent data structures, to build a new Memcached. And it turns out we built a system called MemC3, which achieve 3 times performance. And to store small key value items, we can store 30% more. So how do we do this? Well, before we go to our solutions, I would like to introduce a little bit more about Memcached. Memcached, if you know, it's essentially a key value store, but it's using main memory as the storage. And it provides the hash table-like interface so the clients can talk to the Memcached server over network, and can set a key and a value association, and also you can get a value given the key. As the name suggests, it's a cache. So Memcached try to preserve the LRU eviction order under the space pressure. If the cache is full, you want to insert something, then a less used item will be evicted. Due to the low latency for memory and also the high bandwidth to memory, it is widely used to reduce the traffic to the backend slow database. Well, how Memcached is used? Just go to the next talk. But here I will just try to briefly summarize. It's often used for small key value objects. And studies from Facebook shows that 90% of the keys are smaller than 31 bytes. And some applications even use only 2-byte values. That's pretty small. And also, the front-end servers really want high rate from this Memcached server cluster. So we want to achieve tens of millions queries from the Memcached cluster. A takeaway is we want to optimize for the workloads with small objects and very high rate. And to zoom in Memcached is a very simple program. So it has 2 major components. One is the key value index, and it's implemented by a chaining hash table. Another component is a key value eviction management. It's LRU Eviction, and it's implemented by a double linked list, pretty standard. The problems in this work we're trying to solve is, first is the single node scalability. Memcached originally is designed as a single node, a single thread program. Later on, it is extended to support multi-threads and to utilize the many cores on modern CPUs. However, locks, especially global locks, are extensively used for Memcached in order to protect its shared data structure. So in this work, we're trying to kind of explore how we can use shared data structure among different threads. Another problem we are attacking in this work is the space overhead problem. For each object, key value object stored in Memcached, regardless of its size, 1 byte or 1 megabyte, a Memcached server will just allocate a 56 byte header for this object. And in this header, it includes several 3x3 pointers and a reference count. And if you want to store a 100 byte object, the storage overhead is going to be larger than 50%. So our solution comes from a set of optimizations. The first, we try to come up with a better hash table as the key value index. And we come up with the solution called optimistic cuckoo hashing. By using this hash table, we achieve very high space utilization. Essentially, 95% of the table space can be utilized. And also, it supports high concurrency under read-heavy workloads. So this is going to be the focus of this talk. We also have other sets of optimizations, including we replaced the LRU management into clock-based replacement. And also, we have in addition to this, we have a set of algorithmic and also system tuning to get a better performance. And I will just omit this part. And if you're interested, see our paper. Well, let's go to the detail, how we get such a high space efficiency. This is the default Memcached hash table as we have already mentioned before. It's a chaining hash table. It's very simple. Everyone uses it. And everyone knows it. But it gives very low cache locality because you have to, when you scan the bucket, you have to dereference a set of pointers, chasing the pointers. So it's likely to get multiple cache misses if the hash table is large. In addition, pointers themselves are very expensive. On the 64-bit machine, each one is 8 bytes. So this is not bad. This is not good. Another widely used hashing scheme is called linear probing. Every item is mapped into one position in the hash table. And you just consecutively search available slots for that behind that spot. And it's very simple, so it's widely used. And also, it's very cache-friendly, you can see. The problem is its memory efficiency. Whenever this hash table is more than 50% loaded, it's going to take a long chain for you to search for one available slot on insert. And even it's also the same case for lookup. So the memory efficiency is bad. This is our solution called cuckoo hashing. Basically, it's an advanced hashing scheme proposed a few years ago. And the interesting idea for cuckoo hashing comes from the fact that it associates each item to 2 locations in the hash table by 2 independent hash functions, hash 1 and hash 2. And you just store this item in either location. So lookup is very simple. You just look up 2 buckets in parallel. And the interesting part is insert. I will show you here example how we can insert one item to the hash table. For example, we want to insert the key X to the hash table. We test its first hash function. It tells you, OK, you can insert this item to bucket 2. But unluckily, bucket 2 is already taken. OK, let's try the next one. Next hash function tells you to try bucket 6. Bucket 6 is also taken. So what we do, we randomly pick a victim from these 2 locations. And here we pick bucket 6. And we replace this item in the original location. OK, X is fine, but what we do with this newly bumped out item B, remember B also has 2 locations, and bucket 6 is just one of its home. And we try its next home. And that location is also taken, so never mind, we just do the same thing. We just repeat this process and kick out the existing item in bucket 4 and get C. OK, insert C. This time we're lucky. C finds an empty slot in its alternate location, and we are fine. You may say, this sounds like complex, very complex. But actually, people have proven that the amortized cost to insert one item is still constant. So you just need to look up 2 locations in the hash table. And by doing this insertion, you get 50% space utilized. Still not good enough. What we do is to increase the set associativity into 4. So each bucket now can contain up to 4 different items. If you do this, each bucket is still fitting cache line size, but you can improve the space utilization from 50% to as high as 95%. Yeah, so by doing this, we get a very compact hash table. The space utilization is pretty high. The next problem we are trying to solve is the concurrency. So you may think it's very easy, but actually even to support one writer, concurrent writer, is non-trivial for cuckoo hashing, and for the reason I will talk about. This is called the false miss problem. Imagine you insert something, like you're inserting key X, and the key X kicks out A. Then this item A becomes a floating item outside the table. And if you have a concurrent lookup thread looking for this item A cannot be reached from either its location. Well, even after you successfully replace B by A, then B becomes a floating item. So before you complete the entire insertion process, there will be always one guy floating outside the table. And if you have a concurrent lookup thread looking for that item, you may get a false miss. So our solution to this problem is called two-step insert. And we divide the insertion process into 2 parts. In step 1, we just find a cuckoo path. It's a path to available slot. For example, we are trying to insert key X here. As before, what we do is, without really editing the table, without really kicking out anything, we just mark. We try to kick out A. Then let's try to A. Imagine we just kick out A, and A will be kicked to bucket 4. In bucket 4, it picks B as the victim. And then you imagine you will kick out B, and you find bucket 2 is available. So you successfully find a path from one of the bucket for X to a space available. And we call this a cuckoo path. The next thing you do, you just move the empty slot back. What I mean here is, first, you exchange B and the empty slot. Then next time, you just move A to the bucket 4 to occupy the empty slot. By propagating this empty slot, you successfully move an empty slot to bucket 6, and you can safely insert key X. Then you are done with insertion. So the only thing you have to take care is you need to guarantee each move is atomic with respect to the reader. And how can we achieve this? Well, there are different ways to do this. For example, if we want to move from bucket 4 to move item B to bucket 2, well, one simple way is you can just lock bucket 2 and bucket 4. Then you move the key, and you unlock 2 buckets. Then you are done. Well, we are not really using this way because it also requires the lookup thread to lock corresponding buckets before it reads something. And we think this is not good for read-heavy workloads. Instead, we are doing optimistic locking, and we map each key to one version counter. And before we move that key, we just change the version counter. And on the lookup side, you will always detect if there's any version change during read something. And in this way, the lookup can detect any change. So we're not going to tell you the details, but you can find the details in our paper. To coordinate the different writers, so now we have solved the problems to coordinate the reader and the writer. And to coordinate the writer and the writer, because we take a very simple approach in our current solution, we just serialize all inserts. And this is good enough for read-heavy workloads. And one of our ongoing work is to try to make it with multiple writers. So this is the first part. This is the optimistic cuckoo hashing. In the other part, we also changed the clock, the LRU eviction to clock-based replacement policy. And by doing this, we get better space utilization. Basically, we remove 2 pointers from each object header. We just replace these 2 pointers with 1 reference bit. And we get a better concurrent. We can update this LRU eviction concurrently. Also, we have a set of algorithmic change. So we try to avoid unnecessary full key comparisons on hash collisions. So the problem we solved here is we get rid of the mutex on the get path, and we implement a single writer and the multi-reader hash table. And also, we reduce the 3 pointers with a 1 reference count to 1 pointer to plus 1 reference bit. Let me talk about our evaluation. Here, we try to compare the baseline here is the chaining hash table used by default Memcached with a global lock. And we try to micro-benchmark the hash table performance. Notice this is just hash table performance. So we have multiple threads generating queries to the hash table locally, linked into the hash table statically. And we have the baseline, which is the Memcached hash table with a global lock. And also we change this global lock. We remove the global lock to per bucket lock. That's the easy way to get fine-grained locking. And also we compare with our optimistic cuckoo hashing. As you can see, because the global lock, 6 threads get a very low performance with the base hash table. It's only 1.74 million queries per second. And by removing the global lock, but using fine-grained locking, it gets to 12.79 million queries per second, which is much better. But compared to our scheme, we are still 68% higher than the chaining with fine-grained locking. And this is the case when lookup or hit. We also have the case when lookup or miss. As you can see, we are much, much better than the chaining with fine-grained locking. And this is the reason is because we have some algorithmic change to avoid unnecessary key comparisons. And the last figure I'm going to show you is about the end-to-end performance. So we have the concurrent and the highly compacted hash table and also have a set of change. And we just combine them together and replace the core data structure of Memcached and build a system called MemC3, as I mentioned before. And we try to compare with 2 other different schemes. One is Memcached with Sharding. That is the common practice used by a lot of previous paper. So we partition keys on different cores, and each core is running one Memcached instance for a key space. But notice that because the workload here is zip distributed, basically they have some heavy hitters. In this case, most of the cores will be just idle, and 1 or 2 cores are super busy. And that's why we get a very low performance. The maximum throughput is only 6.6 million queries per second. And it does not really scale as we are increasing the number of threads. On x-axis, it's how many server threads we are using. So we also tried the Memcached with shared threads. And we changed different number of threads we are using, and the maximum throughput we get is about 1.5 million queries per second. And you can see that does not really scale well, and the reason is because the global locking is extensively used for stock Memcached. And for our system, you can see it scales quite well until 12 threads, and the reason is we are running our benchmark on the 12-core machine. And the maximum throughput we achieve is 4.3 million queries per second, which is almost 3x of the stock Memcached. So to conclude, we come up with a hashing scheme called optimistic cuckoo hashing, which gives you very high space efficiency, and it's optimized for really heavy workloads. We have our source code for this hash table available. If you're interested, you're welcome to download it and try it. And we also have more applications. So if you are interested, talk to us in the poster session. Based on concurrent cuckoo hashing and also the other changes, we build a system called MemC3, get much better performance and smaller, we can store much more small objects. So I'm willing to take questions. Thank you.
Chuck from NEC Labs, Princeton. Can I look at one of your earlier slides, introduction, where you talk about the web server, Memcached, and database? Or the early slides?
This one?
Yeah. If you look at the slide.
Yeah, there's a bug in the figure. So I try to simplify the diagram, but yeah, please go on.
Yeah, but my question is not about the bug.
Okay.
Now, in our experiments, the network delay from the web server to the Memcached server and back, that means the round-trip delay for a query, set, or a get, that's typically 4 to 10 times larger than the time it takes to do the lookup on the server.
Okay.
So we found that out the hard way because we first accelerated the Memcached server using a co-processor like Intel's Xeon Phi. Very excited, we got 8x performance improvement on the local thing out there. When we plugged it into the system, we saw that it didn't move the needle at all. So in your experiments, the measurements you've done, did you really consider the full network setup, or you're having all your 50 clients sitting on the same machine as the Memcached server?
There are 50 remote machines.
So what's the network delay that you've observed, round-trip network delay? Is it much larger than the delay for computation of a get or a set, or?
Yes, it's larger than the local computation time, yes.
So what was your setup, network setup that you had?
We have a 10 gig Ethernet switch, and all our Memcached server is sitting behind. All our Memcached server, actually one Memcached server, and all these remote clients are sitting behind this switch.
Yeah, I see what's happening. I think in the experimental setup, it is masking the true network delays that you would see in a real deployment.
So I think network delay is one aspect, but here we are also measuring the throughput.
No, I agree. So what we found was because of the high network delays compared to the computation time on a node for a query, we found out that no matter how much improvement you get on the local server, computation time-wise for each query, it does not really make much of a difference in the larger picture of the network usage. Latency.
So you're talking about latency?
Yeah, we couldn't do
we can take this offline, but basically we found we get a better performance in terms of throughput.
Thank you.
Yeah.
Hi, Arash Molavi from Northeastern University. Interesting talk. I have a question about how you find the cuckoo path.
Oh.
Maybe you talked about this and I missed it. So I was wondering, is it possible that your path will end up in a loop?
Yes.
And if so, how do you deal with that?
Yes, a very good question. It's totally possible to end up with a loop. And the current scheme we're using is we try to kick out things for 500 times. And if we fail, if we can still not find available slots after 500 tries, we just claim the hash table is full. And it is the time the hash table is full.
And you said before you start with your method, you said if your lookup table if it's more than 50% full, then the lookup it's very expensive.
No.
So have you?
Sorry. Lookup is always cheap. Lookup is always as cheap as 2.
Inserting. I'm sorry.
Yeah.
Yeah. So have you compared this? So basically, my question is, how did you come up with this 500 whatever?
This is empirical. We test different thresholds by empirical result.
Oh, okay.
Yeah.
All right. Thank you.
Hi, Sid Sen, Princeton University. I have more of a couple of comments that might be helpful.
Yeah.
So I noticed you used cuckoo hashing with, let's say, 4 items in each bucket.
Yes.
And they're disjoint. So I think it turns out if you make them overlap, you can get pretty good utilization. You know what I mean? Like instead of having disjoint buckets of 4, if you allow the hash locations to overlap by all but one bucket, then you only need 2 locations, for example, to get 95% utilization. So I don't know if that helps you, maybe with compactness.
We thought of this idea before, but we have some other constraints, so we cannot really use it. And the reason is because we do not really store the full key in the hash table. We just store a part of the key fragmentation. So when we are trying to do cuckoo operation, which I mean to kick out some key out, and if we don't have the full key, we have to go to another memory location to fetch the full key and calculate what is the original location. So if we do that, it's going to be tricky. So we thought about it, but I don't see an obvious way to do it. But we can take it offline.
Yeah, maybe we can take it. I don't think I think it's very similar. It's just a different way of laying things out. But yeah, we can talk about it offline.
Sure. Thank you.